Yeah, howdy, folks. So yeah, that title is accurate. I'm basically going to talk about distributed systems, more specifically how we can actually add an orchestrator, what the benefits are. One of the reasons I'm talking about it is because, well, there's a lot of really good benefits to orchestration. I'm not saying it's a great solution to add, because I know that microservice people tend to get super angry when I say orchestration is the right answer, but there are some really good benefits, so it's worth talking about it. Who I am is I am Niall Deehan. This is the coolest picture that exists of me, and I work as a sort of a developer advocate for an open source software called Communda, based here in Berlin. I'm that one, just in case you're wondering. Okay, so the three things that I'm going to basically focus on with distributed systems and the challenges that we face is of course communication between microservices, challenges of asynchronous communication, or asynchronous work that needs to be done specifically, and then finally distributed transactions. How do you deal with the fact that in a distributed system, you're going to have a lot of different systems that do some stuff, and you're going to need to, in some cases, have proper failover and be able to actually undo those things. So let's start with a really simple diagram here. The old days, the good old days, how we had with two systems, we had to do them all. Once upon a time, it was really, really easy. You simply had a transaction, you did the two things. If they were both successful, we continued. If any of them failed, we rolled it back. And it's even easier these days with all sorts of other stuff. And that is, of course, classic ACID transactions. Nothing too complicated. We need they need to be atomic. We need to have consistency, of course, between them. We have to have isolation and durability. This is not new. This is basically what any sort of individual system is going to have, these kind of transactional safeguards. The problem is, of course, that as soon as you start working with a distributed system, you essentially have this very interesting scenario in which those little houses there, the lovely lighthouse and little house there, they would be our little microservices, and we're very, very happy in there. There's where we have our ACID transactions, and actually outside, once we leave that door, that is when we enter essentially the horror show that is the network, and that's when things get way more complicated, and we have to actually deal with that in a big way. There's a really great wiki page on this called The Fallacies of Distributed Computing. Number one, the network is reliable. That's a huge fallacy, so just to remember that. So what this means in practice is that if you have a bunch of microservices, the first thing you have to realize is that when they break, failure will happen and you have to accept it. If everything is distributed, you're going to have some little guys that fall apart. So if you accept failure, the next thing you need to be aware of is you accept failure in one service, but this does not mean that that one failure is going to bring everything down. Okay, that's something you might want to avoid. So we need to actually keep the service is resilient even if one happens to fail. And that means that we need to deal with how does communication work when we have a problem, when that we need to communicate with something that's broken, and how does the client deal with that, and how does the service deal with that when it's broken. So I've just created a really simple example that we'll look at. I've created two little Java Spring Boot applications. One is a payment system that makes you send a REST call to, and it subsequently forwards that to a credit card system to do the charging. Okay, so let me just show you that for a moment. So let's do this. Beautiful. Okay, so this is available on GitHub. I'll show you the link later on, but this is really, really simple. This is just a Spring Boot application. It's got a host there, it's got a REST endpoint, and it simply takes a call, it runs this credit card check, and it then forwards that to another service. Really, really simple. And they're both running here. This guy, and the other one is here. Okay. So this means that if I send a REST call to my service, okay, hey, it works. Who would have thought? Okay, great. We got a 200 OK. That's fantastic. Now, if the other service was down, it would just break. That's not unusual. But there's actually a more interesting thing to think about, which is my credit card service. So the thing I'm forwarding to, let's imagine it's not down. Let's say it's just slow. Okay? So Just a slow service. So what's going to happen? Any guesses? Let's see. Yeah, that's not a bad guess. There we go. Okay. Okay, loading. Great. Okay, it's a 40-minute talk, I think, right? No, so yes, eventually this is loading, 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 and eventually, of course, the service is slow. We don't have a problem necessarily. The service is up, but it's just taking a really, really long time to actually take it. Eventually, it'll find it, and it'll eventually respond, I assume. I don't have that much time, so I'm not going to bother waiting for it. So what the issue is, come on, you got this. Yeah, there we go. So the issue, of course, is that we are sending a blocking request. That's actually the main problem here. I have a service, and I'm sending a request somewhere. The fact that it's slow is an issue entirely because it's a resource problem. I'm now using up time because this request is being sent, and I can't actually do anything. We're blocking up the network, and if you have a distributed system with any kind of throughput, this is a really big problem. And so this is kind of one of the problems, and doesn't scale, of course, which is the main issue. And this is one of the problems with two-phase commit, because if we want to do that, we are just using so much resources that we're actually not going to be able to scale that properly. Now, the best description I've heard from this is actually from Gregor Hoppe, who wrote a fantastic blog post called "Starbucks Does Not Use Two-Phase Commit." If you guys have heard of it, it's fantastic. Very, very simple idea. When you go to Starbucks, you give them your money. They say, great stuff, I'll write your name down. And then they pass the cup on to someone else, and then they take the next order. That next person will then get your coffee for you and give it to you. Fantastic, right? They even have a correlation key. They take your name. It's great. Okay, so in that, they basically do not have a scenario where in smaller coffee shops, someone will take your order, they will actually go over, they will make your coffee for you, and then they will go bring it over to you. Okay, now that is fine, except if a queue starts forming and the person in front of you orders 10 coffees, that's going to be an issue. You're never going to actually get your order in. So the only problem, of course, with this, well, a problem, but the thing we need to rely on is we have a scenario where we have given them our money and we do not have coffee. That happens for a certain period of time. Okay, and in this, of course, we call this a temporary inconsistency. For a little while, we're going to say, okay, here's what you need, and I'm going to trust you guys to sort that out. And I know at the end of this, I will actually have what I need, okay? That's what I need to trust. And this is actually something as part of microservices that people tend to sort of fear a little bit. Because if I want to tell you to do something, and you tell me, no problem, I'll sort that out down the line, but you just wait right there, you may not be totally happy with that idea. But of course, you should be aware that you've been doing this forever. Anyone who uses bank transfers, you may know this is the same idea. If you actually transfer money, there will be a period of time where that money is out of your account and it is not where you wanted to send it. You have temporary inconsistency all the time. The reason that we have a problem with it is because of the possibilities of failure. So because when a client sends something to a service, it can fail at so many points. We have here, maybe the client can end up failing to send it. Maybe the service provider blows up or something, or maybe we get a response from that. Either way, we have to deal with network problems. So in our first solution, in our first scenario, we have our lovely example, and we have the issue that we might have this blocking call. Okay. Now, this isn't a massive surprise to say the general solution to this is if you want to keep those that working, you could use some kind of circuit breaker. Okay? If you guys have used these before, it's not massively unusual. But if I run number 2 here, and my service is still slow, it returned eventually. 1 second. This keeps switching back to weird stuff. Let's. I mean, yeah, okay. It is Windows. That is my problem. But yeah, I mean, it's got other benefits. It's got a good name. Okay, so if I send this, we get this lovely thing here. We get immediately a timeout. The service is slow, so we are going to try and do this. So those of you who might be aware of this probably know what I'm actually using to implement this. It's exactly the same. It actually does have that endpoint is number 2. It still does this charge credit card call. The difference now is that I'm adding Hystrix as a which is a Netflix thingy, who people might have heard of it. It basically says, I'm going to make this call, but I want you to give me a specific timeout. If this thing doesn't actually respond, I'm going to kill this connection. And this actually solves the problem a little bit. And it basically allows us to say, not really change too much of our code at all, but be able to prevent problems like this long requesting that's going to be blocking. So let's see if I can return here again. Yeah. So so failing fast is important because if we didn't have the circuit breaker, it would of course mean that we would have this horrible network that is very, very slow, that we don't really know what's going on. But it's not enough, okay? We actually should think beyond this a bit. And for that, I'm actually going to bring in an example of my buddy and co-founder of the company I work for called Bernd. He is based here in Berlin. And Bernd does a lot of talks around the world, and he tends to use these things. These are airplanes, and they are very, very common, especially for transport. And generally speaking, he gets these at other conferences around the place, and he comes across this problem quite frequently, where he went to try and, on Germanwings, he went to try and book a flight, and he went to try and print his boarding pass, and they said, sorry, it's broken. It's just not going to work. So he thought, well, what is actually happening that got me to this point? Well, clearly Bernd, he made some kind of call through web UI, which subsequently called a check-in. Great. It then probably did something down the line a bit, and this was all synchronous. And then at some point, in all likelihood, something broke. Okay, some service broke down the line when you printed his boarding pass, and what we had was, we had a circuit breaker that then caught that. Now, why do we know there was a circuit breaker there? Because this same thing happened to Bernd on a different airline. And if you don't have a circuit breaker, United Airlines has the answer. So this is what would happen, okay? So we've prepared for this failure, and that's great. Now, what has the designer of this orchestration actually decided? So they've decided that if I get an error down here at my barcode generator, I would really like to make sure that the user gets that error. Okay, that's what we're doing. We're basically saying the user's going to get this error. And why is that? Because the user is really, really good at doing something called a stateful retry. So this is a very, very nice system. It's hard to implement, but don't worry, because users are really good at it. So Bernd, of course, is now, his responsibility is to click refresh on the page until eventually maybe it works, because he owns the state. Okay, and not the best solution. Interestingly, it actually happened on the way back, actually via EasyJet. So this one's actually better. Okay, I'll tell you why. Because with EasyJet, they say, okay, we're having some technical difficulties. Please log again. If it doesn't work, try again 5 minutes. They actually tell you how the retry works. It's amazing. They also say we do actively monitor our site and resolve, so there's no need to call. This is not our problem anymore. This is now your problem. You need to retry, and don't bother us about it. So, yeah. This is what that message says. So what would be a little nicer is if we actually had something that was like this. We're having some technical difficulties. We can't print it right now, but don't worry. We do the retry ourselves because we have your information. We have your email address. We know exactly who you are. We know what you're trying to accomplish. Why do we need to tell you to click a retry button? It doesn't make much sense. So in this particular scenario, what we would like to do is, why not let Bernd do his clicky thing? We'll move the stateful retry slightly downstream to here and basically keep it there. If there's a failure, don't worry, we know what's going on. We just don't let it leave that scope. And that's a very, very simple principle, and generally speaking, people tend to agree that is a very good user experience. It makes perfect sense. And then people immediately say, yeah, that's great, but then I've got one massive problem, and it's this. Because as soon as I actually decide to remove the user stateful retry, I need to try and implement that user somewhere else in my system. Okay, and this is where people get kind of a bit scared. So this is kind of where I want to talk about when we handle a persistent thing in our in this orchestration. We need to then be aware of the fact that it is difficult. It's actually, things get more complicated. For instance, we need to talk about scheduling because now we're holding state. We need to be able to schedule how retries work. We need to deal with versioning. If we're holding state, it means that we need to be able to version. If we change a microservice or something like that, we have to make sure that everything in transit is still going to work, and we can version that. Operating, visibility, scalability, all these things are actual things that have to be thrown into the mix as soon as you want to handle state. Now, one of the reasons I'm here is to talk about essentially the idea of throwing a state machine or a workflow engine to solve this problem, and how relatively easy that is. Now, first of all, the problem with state machines and workflows is that they tend to have this idea that they are somehow proprietary, big, heavyweight things, slow, they don't scale, and they're developer adverse. But actually, there's a whole bunch of really nice open source solutions out there that can help us do this. And they are very lightweight, and they're developer oriented and developer friendly. And therefore, before I go further, I should show you this slide. From here on in, I'm going to just throw some opinions out there. Just be aware. Come to me and disagree after the show. I'm very happy to talk about it. So let's talk about the workflow engines that exist in general. If you've actually tried to orchestrate microservices, you've probably come across something like step functions or something like that. So this is actually something that is going to help progress the state, and it is used quite a lot for AWS stuff. But I mean, it's really expensive. So let's actually look at stuff that is a little less annoying. So interestingly, this is a problem that obviously Amazon have tried to solve, but they're not the only really big company to try and do it, because Uber has a thing called Uber Cadence, which is an open source orchestrator that they actually have open sourced as part of who knows why, and that actually uses it's written in Go, I think, and it's intended for orchestrating microservices. And then Netflix has Conductor, which is, again, their version of this. And this is great. They've open sourced that stuff. It's very, very purpose-built for their particular scenario. And it's not actually a product. They don't have support for it, and they don't really have much of a, it's more of a byproduct than a product. So luckily, there are actually some purpose-built open source engines that are quite useful. And again, I'm specifically talking about ones that I want to be able to embed. I wanted them to be lightweight and scalable, and we have a whole bunch of them here. There's Activity, JBPM, Camunda, and ZB. ZB is if you want to do it at scale. Camunda is what I'm going to be using just now in a few seconds, which is an open source process engine. Okay, but basically the concepts are the same, kind of irrelevant of what you use. So I want to just talk about what the difference between our new system now if we add this new component. So we're adding a huge big component now. I'm adding, my next demo, I'm going to be adding state, retry mechanisms, versioning, and all that sort of fun stuff. So let's see if Windows, that wasn't so bad. Good job, Windows. Okay, so, oopsie. So let's actually take a look at our code now. So the thing I'm actually changing in the code is I am first describing the flow. You can do this graphically, but I happen to do it in Java. So this is basically saying I want a start event, then I want a service task. I want to be able to call this bean, and I also want to give it a specific retry. This says retry 3 times every 1 minute. Okay, that's just describing what I want the flow to look like, and then I want it to end. So there's my flow. The next thing I want to do is I just need to say there's the engine itself. The engine is just auto-wired into the service. I'm just saying the engine, I want you just to create, add this model that I just created. And then not much changes after that. We add this as a component. Okay, that's the same thing as before. That's the same charging mechanism. It still has our Hystrix thing involved in there. And the only difference is that we're actually calling a process to start rather than calling the service directly. Okay, so we're saying start this process. Now, why that's different is because this thing is still slow, I think. Okay, and so if it was normal, well, let's go do this way. If it's still slow, I'm going to run version 3 and send it. Okay, we get a 202 accepted. Great. Relatively rare to see those around, but this basically says that we've gotten your request, thank you very much, and we'll deal with it. Now you can go ahead your business. So we can send this in, and we actually know now that what's happened is the service is slow. So we took that, we committed our state, and now something else in the ether is somehow retrying this. So one of the key things about using the state machines is that they tend to give you some visibility. So for instance, right now, if I wanted to see what's going on, this is a front-end application that you can log in to see what's going on in the engine. It's really simple. This is the thing I built with the code. It's just a little diagram that shows there are 2 instances that are waiting right here and that they're going to run. Okay, so eventually we're holding state here until eventually this thing is up, and then it'll eventually move along. Yeah, at some point. So we now have a thing that's holding our state, and we're able to actually progress the state from there and deal with that. Okay. So let's lower that for a second. I'll come back to that just now. When it comes to asynchronous communication, that's a bigger problem. Right now, we've basically managed to create a really simple holding state. Holding state is not the big problem. Holding state is relatively easy. It's the next problems that are actually more interesting, which is once we hold that state, we need to remember that the services we're talking to need to be aware that things are now asynchronous, and therefore some of the things we do with like right here is that if this guy now has a retry mechanism, we now are holding state here. Great. Okay, fantastic. And this means that if this thing is holding state and doing retries against the credit card system, we have a scenario where we have a credit card system that it can implement retries very, very easily, which means we need to make sure that the service provider is idempotent. Obviously, this is a really big thing. We didn't really need this so much. We might not have needed this so much in the previous example, but this means that I need to make sure that if I send the same request multiple times, it's not going to run that multiple times. It's going to know it's the same request. The best example of this is this lovely thing here. If you ever tried to send money online in maybe 10 years ago, you may remember, we are processing your payment. Don't leave this page. And for God's sake, don't reload. You will end up being charged twice. We do not have idempotency is what this thing says. Now, in a better world, we basically have something like this. We're currently processing your request. Don't worry, it'll happen safely. If you lose connection, feel free to lose time. Again, that's because if we can hold state, we need to be aware of idempotency, and we need to make sure that our service can do that. Now, another thing is that it's possible that our service could actually fail. So one of the things I showed was the idea that I could charge the card, and when it was successful, move on. That's great, but things are not always successful. So what if things have actually failed? Well, if things fail, we can actually catch them, say, we've done enough retries, I'm just going to give up on this one, and then I'm going to just actually send a fail payment message and say, that's just not going to happen. Because as we know, the reason we did that original request was in order to do that. Because again, we have that problem of a distributed system where a whole bunch of stuff could go wrong, and we need to prepare for that. So in our payment case, when we start and we charge our credit card, our payment, we know no retries left, we can then also do something like this, where we can actually say, okay, well, we need to actually refund because it's possible because this thing did send the request, it's possible the request broke here, or in the worst case scenario, the request broke here. So actually it's been successful. We just don't know about it. So in that case, what we can deal with it really easily by saying, okay, if we have no retries left, we'll give up, we'll send a failed payment, but then we need to actually run this retry. I'll talk more about that a little later on, but we can do it reliably. It means that this is also holding state. I will be able to say this refund will happen because if it fails the first time, I'll just eventually wait until it's back up and it will happen. So if Bernd had his little check-in process there, which generates the barcode and that sort of thing, the first thing that people tend to talk about is, when we suggest this idea, is that the customer wants synchronous responses. That's just what they expect, okay? And the interesting thing is they don't ask, well, if the customer doesn't get a synchronous response, what would they like? Would they like just an error page? Well, that's not really a very good idea because luckily HTTP has a very, very nice idea, which is really simple. In some cases, the services will be up and we can get back at 200, okay? And in other cases, we should just say, instead of breaking everything, say, okay, we couldn't do your thing right now, so you will get a synchronous response or potentially not. So let's head back over here. Okay, so in that next example, if I turn my service back to normal, great stuff. If I send version 4 now, okay, I get 200 okay. This was able to process it. The service is doing fine. We didn't need to worry about it. And then if suddenly the service goes slow, we get our 202 accepted. So now we need to hold state because now we're saying, okay, well, we're not going to break everything. We're just going to tell them, well, we're working on it. Don't worry about it. And you will eventually get that request. We'll take care of it. Okay, this is a much, much better way of actually dealing with these kind of responses. So, so this is, of course, a much better idea than saying either it's synchronous or everything breaks. We have other options. Okay. So another challenge, of course, is this really simple one, which is if I send a message and I don't get a response back, if we have idempotency, we generally don't want to have to, we generally want to wait for a certain amount of time, and that's a really important one because timeouts are just as important as catching errors. If we send something and we don't get a response in time, we need to actually be able to deal with a scheduled timeout that can make sure that in this time the failure never leaves the scope. So we can say, we sent this message, we know how long to wait, and that's actually quite easy as well. You can draw that. It looks something like this, where you would have, we send our generated barcode, we wait for our process, and we then have here a little timer event. And this thing basically says, okay, all of this is in state, so that means we know exactly how long we're waiting for, and we can have these guys just handle the time. They can say, okay, if an hour has passed, we will actually just resend a request again. Because we can do that because we own the state. And these are actually for individual tasks. So we generate the barcode, wait for the barcode, and that timers are scoped. They're saying that timer will only exist if we're on that state. Okay? So once we leave that state, the timer doesn't matter anymore, which is quite hard to do, but it's quite easy here. But also another thing we can do is we can increase the scope, but we can say, okay, well, this is a timer on the entire process. We're saying we are waiting 4 hours. If 4 hours elapses during the life cycle of this process, no matter what's happening, I want to just stop it and just make sure things are able to progress independently. Now, this notation is called BPMN, Business Process Modeling Notation. Who actually here knows BPMN? Just as a show. Hey, awesome. Popular stuff. It's an open standard. It's been an ISO standard since around 2012. The point of it is to be able to visually create a sequence of workflow events and activities and be able to maintain that in an executable model. Because the thing you draw in BPMN is directly executable. That's the key. So that if I were to draw it with an analyst and say, here's how things should work, if I then deploy it, it's exactly what you see as as an admin as well. So it's pretty easy to understand. It's executable, mature. There's lots of tooling for it. A bunch of those open source engines I showed you earlier, I think they almost all use BPMN as a notation. And there's loads of modeling tooling and engine tooling as well. It's a really good standard. Yes. No, we can though. The graphical tool is represented in an executable XML model. It's actually not a graphical tool. I'm actually glad you mentioned that because I do have that slide here because I predicted that question. Yeah. So now let me actually. I will answer that in a moment because you're right. It actually is a bit of an issue. Graphical tooling puts people off quite a lot because the only thing it's good at, and actually I have a good example of that, is this is a Clem Investors article from a while ago. This is discussing Saga pattern, okay? And the really cool thing is that he has a little picture up here that shows how Saga works, okay? We want to book a hotel. We want to do this, this, this. If that works, we need to undo that. I'll actually talk more about that later on. But the key thing is that he basically has a whole bunch of code all over this, okay? Of course he does. It's an article and he's talking about how we actually code this. But the key thing is that this is the thing he leads with because before I need to read the code, a graphical understanding of what happens is fundamental before you start reading this stuff. It's really useful. The problem with the graphical notation is it's just a picture, okay? It doesn't actually do anything. It's a representation of the code. You make the code first, then you make the picture. With BPMN, it's actually living documentation. So BPMN is actually executable. If you draw it, it's what actually happens. So it's never out of sync with the code. It is the code. And it can actually be used in lots and lots of different ways. One of the ways is that this is a visual report on a test case. So this is showing I ran a JUnit test that tested a certain flow in my process, and this shows me how much was tested. Then if we go into operations, we could actually then see, okay, here's what's actually happening in my process. I can see exactly how many instances or how many states we're representing here. We have about almost 5,000 in the first one, about 2,000, and also importantly, we can see where errors are, which is around the 200 and something, 300 mark there. So we actually have a visual representation of exactly what's actually happening, and this is executing. This is not a picture of code, it is the code. We also have this guy here. This is actually taking that data that we saw that's produced by moving tokens around and just creating simple reports saying, where is the most common path that we go? Where do we actually end up in our process? So you can actually, as well as using it as an administrative tool to actually see what's happening and where you are across your distributed system and what has happened, because you also get history of it, you also get to see, well, I want to try and get some nuanced understanding of what's going on with my distributed system. What paths do we take the most, and how can we improve in future? As it happens, this isn't the only visual indicator. Step functions has its own one as well. A visual indicator of what's happening in a distributed system is really, really important. It's also something that lots of different people have actually tried to implement as well. The reason I prefer BPMN is simply because it's a agreed upon ISO standard, and it goes together very, very well, and it is directly intended to be a notation that is executable. You can do really complex stuff with it too, and I'll talk more about that a little later on. So let's recap to where we're at this point. We have a client, great stuff, which does retries and timeouts, and we also have a service provider that can actually do item potency, which is fine. So right now, we have a scenario where our service that has the engine is making a REST call to the service there, which is great. Okay, so we are just making those calls. We could also be doing something like this, where we have some kind of bus, like maybe Kafka, maybe RabbitMQ, some queuing system, and this thing eventually says, instead of a REST call, we'll put that there, and then it'll get picked up. Okay, now this is actually quite good, but I actually prefer if we think about inverting this a bit. So there's a fundamental issue with actually trying to poke another service or tell it to do something. And that is, and instead, it's actually much nicer if we can say, this service, when it's alive, simply should just get work when that work exists. I could say it registers for a topic or something and then picks it up and then does it, okay? Rather than the client making a REST call to it. One of the reasons why it's a good idea is because it avoids this lovely problem, thundering herds. So if you guys have come across this before, this is a fascinating problem where if you have a system that is making a call to another system, and you have a whole microservice and everyone's making calls to other microservices, that's all great, except that I think a couple of years ago, AWS had a 5-hour outage, and this was a thundering herd problem. What had happened was a very small component in their distributed system failed for, I think, about 15 minutes. Okay, and it was small but important. Yeah, like me. And eventually, when it came back up, lots of other systems just blitzed it because they had this retry mechanism. Okay, they were at a state and they were waiting to just retry it again because they know it was down. And when you have such high throughput, you get all of these things hitting it as soon as it comes back alive. It just crashed again. So thundering herd happens quite a lot when you actually implement these retry patterns and state handling. Which is why I also have a fun picture of, oh, there he is, Niall's glory. Well done. Yeah, so, which means there's a lot of other ways of using the engine. So the engine could actually be, let's say, deployed to the service. It could actually be an independent component, another microservice. So the microservices would essentially subscribe to a queue of stuff they need to do and then pick that up, and then they could actually write back when they're done. Or you could have a worker that fetches from the service. In either way, it's a little nicer if you have a nice centralized bus anyway. So now on to this lovely topic here. This is actually one of my favorites. This is distributed transactions, because this always causes issues when you actually have lots of things that like to happen one after another. And as I said, failure is something to deal with. And I'm going to use the usual example, which is I'm going to use the classic booking stuff, which we saw earlier. So in this scenario, we book our hotel, we book our car, we book our flight. All makes sense. And then, of course, the flight fails, and we no longer, because for whatever reason, we couldn't book that flight, and therefore we need to cancel the car in the hotel. Okay, so this is Saga. So this is a really simple way of undoing stuff across microservices. And there are usually two alternative approaches. We actually have choreography and orchestration are the two ways in which people try to solve this problem. With choreography, every service knows the one before it and the one after it, and to undo something, you simply follow the trail back. So it looks like this. If this was a choreography-driven one, I would send my request in. I would then do my hotel thing, do my car thing, get my flight thing, and then great, flight fails. Oh, sorry, flight successful, great, and now the trip is booked. Okay, so that means that we just go on this thing. Every single service knows where to expect the request and where to put the result. If, of course, this fails, then it needs to follow the saga backwards, which means the flight needs to tell the car, which needs to tell the hotel, and so on and so forth, and then we know we're failed. Okay. It's actually just a diagram. They could actually be using a bus as well, but the same principles are true. They would still be actually sending some message to something that eventually gets to the next service. I'm getting there, don't worry. Yeah. Okay, so in this scenario, we basically have this lovely thing where we have a basic agreement with the we change this process slightly because now we've agreed the car rental one, we're going to swap sides. Usually the flight is last because it's the one that costs money to cancel. Usually canceling hotels, you can usually do for free. Sometimes car companies, we don't really know. But if we wanted to change the order, wanted to flip hotel from car, we basically need to change absolutely everything. Because everything then needs to change the order in which it actually sends a message. Okay, because any change is going to affect what happens before and after it. So I think basically we have what we tend to expect is something like this. It sometimes gets a little bit crazy. So the alternative would be orchestration. In orchestration, as you described, we basically have the simple way of saying, we're sending a book hotel, and then we will get a response. Once we get that response, we'll go ahead and get the next one, and so on and so forth. What we have here in trip is a single point that is deciding what to do next based on whatever results from the previous microservice, and eventually trip is booked. If we wanted to change the order of anything, it all changes here. Not only does this own the order in which things happen, it also has the state of what has happened and what will happen. Everything is dictated here. And so in BPMN, you would just write something like this. So in BPMN, we have our reserved car, book hotel, book flight, and right below it there is the compensation tasks that we can then execute if an error were to happen. And again, this is all done statefully. Okay. So yeah, so you can also, of course, have a workflow as part of a service. In my example, I had trip as a service. So the workflow is just embedded in there. It's another service, another microservice that just actually controls what the state's going to do. And you can also have those in other services as well. Every service can have its own little microservice. And so what I want to show now is some compensation stuff. I think I have time for it. How long do I have left, actually? Not bad. Oh. Awesome. Okay, so if I send this request, I get my lovely 200 OK. Now, version 6 is different because version 6, if I take a look at my processes here, version 6 looks like this, which is we do our process, we deduct some credit. In some cases, we charge the card. If the charge is unsuccessful, we throw this event. This is important. This event basically says, if we get to this event, I want you to look at where we have been in the process and find the corresponding tasks that were successfully completed with this corresponding symbol and basically run this. Now, the engine's in charge of actually doing all that logic. Let's take a look at what's going on. So we have some historic instances here. If I send a few of these guys. See, and let's see what happens. So we have 10 started. We now have 13, and we see that 9 arrived here and 3 arrived at this point. So if we wanted to find out, we see that the corresponding 3 of these and 3 undos. So if I select this guy here, let's pick one of them. So this is the specific instance. So we now actually have a visualization of what actually has happened, of course, a certain orchestration of a service. We have here that this thing obviously failed. The orange little one there indicates that this task was not successfully completed, but we got to that state. And this shows that we actually ran down here. We then triggered this, and we're able to undo that call. And again, all of that was done statefully. The model itself is kind of interesting because I think in this one, I think I might have actually built it. Let's open it up. There we go. So the model that I actually built for this, I didn't build in code like the first one. This was actually built in a modeling tool like this one here. So I was able to just essentially, put some stuff together and click some things. And then eventually you'll see that I have I have various implementations here on these. This is saying that an external task is doing this, and this one here is saying that some delegate code is running here. The difference here is that the delegate code charge card is the thing that I had locally. It's actually the thing that's part of my project here. It's it's right here. It's a component somewhere. There we go. It's a specific component, and the other one is called external, and it just has this thing here that says customer credit. Now, that's actually what I described earlier as being the fetching mechanism. The engine itself doesn't need to be sending out stuff. It can simply hold the current state, and right now what I have is I have this little guy running, and this little guy is a little service that subscribes to this topic called credit card. It just says, I will do that work when it shows up. So if I kill this, which I hope I can, there we go. And then I decide to start some of these. They will all start. That's not a problem, okay? The difference would be that now we should see that the engine itself is holding the state here. So the engine says, okay, I'm just holding this. There's another service that is essentially going to pick this up and do it. But the engine's not going to tell that service what to do. It doesn't know where it is or how it exists. Instead, this service here, once I start it up, well, it's a little Node.js thing. It simply subscribes to that topic and then picks that work up whenever it gets up. There we go. It picked up those things and then continued the process. So this is a lot more decoupling. Alrighty, so we have the client now that can implement timeouts, retries, and compensation, and the service provider also has compensation and idempotence. Generally speaking, if you combine those things, you can kind of solve a lot of these problems. And the important thing about that is we can all do it reliably because we always have the state controlled by us. So the final points I want to leave with you guys is be aware of the complexity of distributed systems because they're way more complicated than people tend to think. Know your strategies and tools and how to handle those, okay? Like retries, like compensation, like idempotency. And also take into account that it's actually not that complicated and quite lightweight to add things like circuit breakers, historics, and commanda as stateful retries or other workflow engines. Okay, so thank you very much.
Thank you, Niall. So, some questions, please?
I'm surprised your hand didn't go up faster.
Hi.
Hey.
Thank you. Suppose that a given company has many applications plugged in with queuing systems, and they have implemented almost very similar logic to this, but they are not using the state engine. So they have the logic distributed in the code of all the applications. Yeah. Is there any easy way? Any recommendations on how to port it in?
So it's
How
actually
to
easier
bring
than
it
you
under
think.
control?
Yeah, I've actually done that before. I've gone to do little workshops where I've helped. It's normally around services that have the choreography problem, where every service or user interface knows what happens next, and it's actually easier than you think. It's mostly about deleting code, because the core thing you want to keep is just the business logic. The thing you used to need to strip out is you need to strip out the subscription to that previous task or producing the event to the next thing. And you just remove that and make that way more generic. So instead of having, let's say, I'm waiting for something on this port or whatever, you could simply say, this service will now register for this topic instead, for instance. And then instead of actually knowing what happens next at all, like instead of having to write something that needs to send a REST call to the next service, you just delete that, and instead you just write a thing where I'm going to send either an event to a queue, or I'm going to send a call to the engine or something. So it's actually less complicated than you would think, because it's not about adding anything, it's really just about taking stuff away from your services.
Hi.
Hello.
Thank you for your talk. You had a nice slide about the car and hotel booking where you first had. Well, your slides are very beautiful.
Thank you.
Yeah.
Yeah, I read up.
Where you first showed the choreography approach as you described it, and then the orchestration approach.
Yeah.
My understanding was right there. That's perfect. So on the orchestration one, you were sort of trying to convince us that you felt the orchestration approach was superior.
Yes.
Okay. So I agreed with you that the diagram was superior. But I don't agree with the fact that it has to be orchestration. I think that you could do that second diagram in a choreographed way, where you simply have, you push the algorithm to initiate to everyone, and anytime any one of them fails, they put a flag in a standardized place, and everyone is watching that flag, and if anyone sees the flag, then they all independently know to roll back.
Yeah, so the only problem with that is that, again, it's, I think I might have mentioned this before, but the issue with that is that it violates some principles of the microservice architecture in general. So the idea that every microservice should be independent of any other. Now, if every single microservice must have a component that must know the choreography, you're basically limiting every microservice to a specific language, perhaps, or a specific data source, perhaps. And this might actually be a little bit of a, people quite like domain-specific microservices and the ability to be able to choose that in my domain, this particular technology is better. I think as soon as you start like doing something like saying, okay, your microservice, before you even start, needs to implement these particular things, then you can write whatever you want. People tend to dislike them. Now, I don't disagree with you. I think I don't love all the principles of microservices, but I do think that people tend to push back on that when you start to say, I have a great idea for your microservice, and it starts with you installing this thing onto it. That's
Provide a standard API the way you do with logging and so on?
Pardon me?
Can't you just provide a standard API that gives a few of these primitives in addition to
You would, but
logging
then-
and the other primitives that you
But
already
yeah,
provide?
but then you wouldn't actually need to have the orchestration on the microservice at all. So you would have a single microservice that simply controls, like an engine that controls the state, and then every other microservice is irrelevant. So then when the state changes, no other microservice needs to care about this flag or about loading anything up. And also they have versioning as well embedded in there, because that service takes care of versioning and takes care of the retries. Every single service then is completely independent of needing to know about any state transitions. So I think it would work the same, but it would just have the engineering in a different place.
Thank you.
Cool, thanks.
More questions? All right.
Okay. Yeah.
Great talk. Thank you.
Thanks so
Niall.
much.